consensus first slide will show. Thanks.
Hey everyone, I'm Sam. I guess the purpose of this talk is to give you some sense of what you could talk to me about. So I'm going to try to give you a little bit of an overview. I'm interested in a lot of things, broadly computational statistics, but lots of aspects of it, robust statistics, Bayesian statistics, lots, all things high dimensional, a lot of heavy-tailed statistics. And I actually have broad interest in theory of computing beyond that. So the world is full of statistics problems. Some of them seem to be computationally easy. Some of them seem to be computationally hard. Like for some reason, if you plant a clique of size 1/3 in an Erdős-Rényi random graph on n vertices, it seems like it's computationally hard to find it. But like if you plant a clique of size root n, then it's like computationally easy. And that's like kind of crazy.
Just make the figures.
What's that?
You should flip the two.
Yeah.
Yeah, you should flip the two. Thank you. That's a good. I made that slide 2 minutes ago, so I really appreciate it. Thank you. Yeah. So my standards for accuracy in research are very high. Anyway, this is the edge of tractability between easy and hard problems. Sorry, everyone. And a major goal of my research is to figure out, where is this edge? What are the best algorithms? And what are the reasons that problems become hard when you cross it? So there are kind of two themes as we approach the edge of tractability from both sides. And I think about both in my research. The first theme is algorithm design. Where the goal is to understand where the edge of tractability lies by designing computationally efficient algorithms for statistics problems with the strongest possible provable guarantees. And ideally to do so using unified algorithm design principles. And the set of algorithm design principles that I think about a lot goes under the name the sum of squares method. It's a way to utilize powerful convex programming techniques coming from mathematical optimization to solve statistics problems. And that's something I'm happy to talk to you about. It's seen a great deal of use in algorithm designs for computational statistics over the last 5 years or so. So I thought I would give you a really quick example of a result of mine from a couple of years ago using this sum of squares method to solve a very basic problem in computational statistics. And even though this result is now a couple of years old, it's inspired a lot of work of things that I've worked on, also actually some things that others have done using the techniques to design algorithms for less simple situations. So this is a result for a very simple problem. I want to estimate the mean of a high dimensional random vector. So I'm from independent samples. So there's some probability distribution D in high dimensions, like little d dimensions. I get some n independent samples from it. I want to estimate its mean. And all I'm going to assume about this distribution is that it has bounded covariance. So it might not even have a third moment. So the third moment might be infinite. I would like to estimate the mean by some estimator mu hat. And I would like to get small confidence intervals for the mean. So I'd like mu hat to be close to mu with good probability, with probability like 1 minus delta. And the reason for this funny expression, this is the distance that you should be, is that this is the distance that you would be to the mean if you made a stronger assumption, the vector is Gaussian, and you use the empirical mean, which would be the optimal estimator. So these are the best confidence intervals that you can hope for. And the question is, can you do this while making much fewer assumptions on the underlying random variable? If you just assume that it is bounded covariance. And the empirical mean won't do it, right? The empirical mean is way too sensitive to outliers in your sample set in order to obtain this kind of confidence intervals when delta gets small. The empirical mean is basically only great if x is sub-Gaussian. It turns out, though, that if you use a more sophisticated estimator, if you use some notion of a high dimensional median, you can actually kind of remarkably achieve this. This was a result proved only pretty recently by Lugosi and Mendelssohn in 2017. So even though this is a problem that could have been stated, by Pearson pretty much, like this was only resolved like 3 years ago. So you can use some high dimensional median, which gives you these statistically optimal confidence intervals, at least up to the hidden constant. But it seems to be computationally infeasible, like Tukey medians and things like this isn't exactly a Tukey median, but it's sort of Tukey median-like, and things like that, are very computationally expensive. So the result was that it turns out that you don't have to employ the computationally intractable version of high dimensional median Actually, there exists a polynomial time algorithm that achieves these same information theoretically optimal confidence intervals, making only the assumption that the underlying random vector has two finite moments. So there's essentially, like, one way to view this is that there is not only is there no statistical cost to being robust to these very weak assumptions, there's also no computational cost. You don't have to spend exponential time or anything like that. And as I hinted at before, the approach to design this algorithm was not ad hoc. It's really based on this unified technique for algorithm design and statistics called the sum of squares method, which I don't have time to describe in any detail, but I'm very happy to talk to anyone about. Okay, so can anybody spot the bug in this slide? Okay. So we said that the world is full of easy problems. The world is full of computational problems. Some of them are easy. Some of them seem like they're hard. And the second theme in my research, I have like 3 minutes. Is that right?
Yeah.
Okay. The second theme in my research is to approach the edge of tractability from the other direction. And in statistics, this is kind of a new field. How do you show that a statistics problem is computationally hard? What kind of evidence can you establish for it? Well, that's sort of what this program is about. But a kind of evidence that I've thought about a lot is if you have unified, powerful algorithm design techniques that seem to capture the best available algorithms for lots of problems at once, then unconditionally ruling out algorithms based on those techniques for a seemingly hard problem is at least strong evidence that to solve that problem, you would have to invent something totally new. And maybe it's even evidence that that problem is straight up computationally infeasible. So my work is focused on doing that. Actually, one piece of work I did now 5 years ago was exactly about this planted cleat problem that I mentioned on the cartoon slide, where we showed that this sum of squares method is not able to do things like find n to the 1/3 size cliques in Erdős-Rényi graphs. And instead of telling you an example thing that I proved on this theme, I want to tell you an example problem that I really like. We heard a little bit already, probably at the boot camp, about hypothesis testing problems in high dimensions, which are not solved by looking at low degree moments of the underlying distributions that you want to test. So there's this low degree conjecture that's floating around that says that if low degree polynomials don't solve some high dimensional hypothesis testing problem, think just like an Erdős-Rényi graph versus an Erdős-Rényi graph with a planted clique, there's this very strong conjecture floating around that says that's actually, if low degree polynomials don't solve the problem, then polynomial time algorithms don't solve the problem. And I would love to establish some version of this conjecture unconditionally when you restrict from polynomial time algorithms to sum of squares convex programs. We could hope to unconditionally rule out these powerful algorithms under a very mild criterion on an underlying hypothesis testing problem. So a major goal of mine this semester is to try to make a little bit of progress on this sum of squares version of the low degree conjecture. And I'm happy to talk to people about it. In case you don't want to talk to me about those things, you could talk to me about discrepancy. I'm super into discrepancy recently. You could talk to me about combinatorial optimization. I've thought a little bit about indistinguishability obfuscation in cryptography. And I also really like to talk about and ride bicycles. So you can talk to me about that too, if all else fails. Finally, a super short plug. We have a workshop on a lot of this stuff next week called Rigorous Evidence for Information Computation Trade-offs. There's going to be a lot of awesome talks. And I promise none of the speakers are going to invert easy and hard problems like I did. So the talks will be super accurate. Great. I hope to see you all there. That's all.
Thanks, Sam. Yeah, there's a super quick question. Otherwise, we'll just keep
Keep the party rolling.
Yeah.